So TLS and cryptography. How many people here have used TLS? I am going to be so surprised if the rest of you has not used TLS at all. TLS is used for every communication you do. So if you've ever been on the internet, you've used TLS. How many of you have done some cryptography by yourself? Looking into details, that's few. Well, that's good. That's why we're here. So most of the times, TLS and cryptography are talks by math people, by people doing a whole lot of explanation on how exactly to calculate things, and not much on the actual implementation of it. So I figured we need to have a talk about the opposite. Let's skip the math and go to how to implement it, how to figure out how things work, with just enough cryptography to understand what we're doing. So why do we even have this whole cryptography stuff? Well, deep down, we're just trying to communicate. We have two people, Alice and Bob, and they just want to exchange some information. Now, every time I show people Alice and Bob, the first question is, who's Alice? And Alice, in this case, is an archetype. She's basically a representation of the archetypal person that is trying to communicate, and Bob is the archetypal other person trying to communicate. It's a bit like a stereotype, where it's like an oversimplified way of looking at somebody. But I'd like to give you a very concrete idea of who Alice and Bob really are. So let's go back to a different Alice and Bob and see what they like to talk about. So meet Alice, Alice Cooper, and Bob Marley, and they like to talk about music. And there are some things that can go wrong in communication. In this case, we're not looking at the communication between them and how that can go wrong directly, but we're looking at how somebody else can profit from it. So we have somebody who's eavesdropping. We call her Eve. No, not Eves, eavesdropping, like that. And eavesdropping is the idea that somebody is trying to get the stuff that you're communicating about without you realizing that something happens. It's the model where you're not able to change anything about the communication, you're not allowed to interfere, but you can see everything that they send out. So to prevent this, we can hide our message. We can encrypt our message, changing it into some kind of code so that nobody sees what's in it. And by having both sides have the same information on how to decode it, the intended recipient can read it and nobody else can. We can also hide it in a much more simple way. Just literally hide it. Stick it in a place where nobody would look. We can put it on a piece of paper with milk, writing it down, and then instructing the other side to take the piece of paper, heat it over a flame, and wait for the message to show up. But all of these methods depend on the other side knowing how to read it and nobody else figuring it out. So this is somewhat limited. Fun fact, these are both pictures of Lena. Anybody know Lena? Lena is one of the copyright-free images that is used a lot in photography. The one on the left is just Lena. The one on the right is Lena with a baboon. But if I didn't tell you this and you didn't know how to get it out, you would never realize. It just looks like a picture. But even having information exchanged between people gives you information. Because if I know that Alice and Bob are communicating, I might expect to see some album come out from Alice starring Bob. So just knowing that two people communicate, I know that they have something to communicate about. If I see an encrypted message between two parties, I know that they have something important to talk about that I'm probably interested in looking at. And this happened a lot, even in the Second World War, where people in the field, every time you send a message back to the base, people know that you are communicating. And looking at the frequency of transmitted communication can tell you when an attack is coming in. So a thing that they used to do was to distribute about 10 radios to each side on the front and give people the chance to send messages back home. All the messages going back home are encrypted, like everything else is. Because at that point, every day there's 10 messages going back home. And nobody's any the wiser. Then there's a different kind of attack. And this attack is from, well, you know, some guy who's trying to interfere. And we tend to call him Mallory. Mallory is the kind of person who sits between the two. He is the attacker in the middle. It used to be called man in the middle, but any other gender will work just fine. And they are trying to make sure that they don't communicate what they think they are communicating. So while Alice might have some really complicated music, Bob might just be listening to Mary Had a Little Lamb. They're making it so that they aren't communicating with each other, but with Mallory instead. So as Alice and Bob, how do we make sure that we communicate about what we're trying to say? Well, when we send a message, we need to include some kind of way to check that the message is authentic. It's from the person you thought it was. And we can do that with signatures. We can do it with royal seals, like the one we have over here. We also want to know that the message is the message that was sent, and not just somebody else's message in the same envelope. So we check handwriting. Is this the right handwriting? Is this the right kind of message? Does this make sense? And we check that the seal is unbroken. It hasn't been tampered with. Nobody's taken out the field orders and replaced them with everybody go home and enjoy your lunch. Which brings us to identification. How do we even know who somebody is if we're not seeing them? We have some kind of identity validation. And in computers, we have this a lot. We have password validation. We want to know that the person trying to communicate with us knows some bit of hidden information. We want to have shared secrets between two parties communicating so that they have some kind of secret to use in communicating and nobody else knows. And in some cases, it's enough to just see that they have a passport. But how do we do passports in computers? So now that we know why we want cryptography and TLS at all, let's go into the meat of it. So we're going to talk about asymmetric cryptography. First we do RSA, then we do elliptic curves. Then we're going to talk about hashing, then passwords and hashing, because while not directly related, passwords and hashing is often done wrong. We'll go into signatures and certificates, and we end with symmetric cryptography. And we might have some random topics pop up. So RSA. RSA is something that we use a lot for passwordless login to computers. How many people here have used terminals? How many people have used terminals and remote access? There we go, that's a lot of people. How does it work? So the idea is for remote login is that we have some kind of information that the server knows about us. It knows how to verify that we are us. And we have some bit of information that allows us to prove who we are without handing it over. Which means that if we identify ourselves to a server, the server doesn't have information to identify to a different server. So we generate a key pair with SSH keygen. We place the public key part of that in the server somehow, because it's unspecified how you do this. It has to be somewhat safe. But after that point, you can use SSH to log in remotely without a password. But at that point, we're not sending a private key. You can't send a private key and then expect the other side not to keep it. There has to be something else. And that something else that we're doing is a zero-knowledge proof. So let's dive a bit deeper. We're doing RSA, and RSA is done in a ring. A ring is a mathematical construct, and this is about as deep as we're going into math. It's a math construct where we have a set of numbers that have operations, typically a plus and a multiply, that are closed over the ring, which means that anytime we add two numbers or multiply two numbers, we'll end up with a different number that's part of the same set. And the ones that we're interested in are the ones with finite numbers of numbers. The typical way to do this is to take the remainder after division. So let's take a simple ring as example. We'll take the numbers from 0 to 4 modulo 5. 1 plus 2 equals 3. We know this. 3 and 4 equals 7. But 7 isn't part of our ring. But 7 modulo 5 equals 2. We subtract 5 from it, remainder is 2, and 2 is in the ring. 3 times 3 is 3 3s added together, which is 9. Modulo 5 is 4, which is again in the ring. We can even do exponentiation by repeated multiplication. 3 to the power of 4, 4 3s, is 81. Modulo 5 is 1. So within the ring, we can do some bit of math. And this exponentiation is essentially all there is to RSA. We take a number, we exponentiate it to some other number that's hidden, and we get intermediate results. And then we somehow do the inverse in the ring, and we get the original data back. So let's start with a simple example. Calculators at the ready? We'll take some small bits of RSA. I mean, we're not doing 4,000-bit RSA because calculators aren't that hard, so let's start. let me know when you finish typing. You don't seem to, is this too large? Okay, maybe let's go for smaller numbers. How about 31 and 37? Let's do 10-bit RSA because that's a thing we can follow. So we take P is 31, Q is 37. These are the two parameters within RSA that define our ring. And the ring is defined as a ring over modulo n, which is the product of P and Q, which is 1147. Then we have the size of the ring, roughly speaking, which is lambda of n, which is 180. That's the product of the 2 minus 1 divided by the greatest common divisor, or the least common multiple of 30 and 36. Then we have E, which is our public key. We can pick this as just any number, but the number needs to be co-prime to lambda n, which means that it doesn't have any common divisors. And then with a bit of math, the extended Euclidean algorithm, which we're not going into, we can get D, which is the inverse. So let's see that that works. We'll take plain text being 73, which is the letter I. And we're going to encrypt this. So the crypto text is 73 to the power of E, to the power of 7. So it's 73 times 73 times 73 times 73, and so on, mod n, which is, with a little bit of math, 850. That sounds nice. So now if we take that and raise this to the power of, where is it, 103, we should get back 73. So let's go and do some exponentiation. Okay, I'm bored. This is too many numbers. Especially if we go to 1024 bits, this is just going to take forever. So we need to do something more clever. Instead of multiplying every number, let's reuse the results that we had before. So instead of multiplying 850 times 850 times 850 times 850 times 850, let's see if we can square the numbers and just store what the results are. So we start by 850, we square that to get 1037. 1037 squared again, 630, which is actually 850 to the power of 4. And if we do this a couple of times, we can get 850 to the power of 64 in 6 steps with just a single multiply every time. And then with these 6 steps, we can take the number 103, pick out which bits are set in our private key, and multiply those together, which is 850 to the power of 103, which is a multiplication of 850 to the power of 64 and 32, which is 96, plus 4 is 100, plus 2 is 102, plus 1 is 103. And we do the math, we look them up in the table we just had, 850 times 1037 times 630 times 1037 times 630, modulo n actually is 73. So great, we can exponentiate numbers. What does that do? Why do we care? Well, we care because we had a number that was public knowledge, which is E. E is 7. We have a different number that's public knowledge, which is N, 1147. And anybody can take these numbers and calculate the encrypted form of some plaintext. We took 73, made it 850. But nobody else can take 850 and get back 73 without just trying every possible private key. If we want to get D, you need to do a discrete logarithm to just do the inverse of encryption. And there is no efficient way to do this in general. The alternative is to take 1147, split it up into both primes, and then just calculate what the private key should be, which is actually impossible. We'd need to factor a large number, and that is, in general, an unsolved problem unless we go for quantum solutions. We're not going into quantum cryptography here, that would go a little bit far. So for RSA, we have a public key, and that's just a tuple of N and E. We have a private key, which is N and E, plus our hidden number D. And this will work as a private key, but usually we also store P and Q, because you can do a bit more fast math with that. It allows you to shortcut something and compute it in half the time. Given this, we can explain how you log in with SSH, because my server has a public key, N and E. The server sends us some random number encrypted, and only if we have the key can we provide them the plaintext. which means that we show them that we have the private key, but we don't provide them any knowledge gained from that. They just know that we have it, which means we can log in. They can't reuse the result anywhere else. They don't get a private key. We're actually securely logged in. I know this is nice, but 10 bits, it's a bit short. And factoring 1147, if you have a calculator, you can do that just by brute force trying a bunch. 32-bit RSA is nice to implement. If you want to make a unit test to see if you got the math right, that's nice because multiplications are just 32-bit numbers multiplied. 1024-bit is the absolute minimum that you should use to have any kind of security, and even that is too short. Most places nowadays use 2048 or 3072 bits as a minimum, with 4096 in many places used, and even 1000 or 15,360-bit encryption being used. So how do we scale up? Well, we have to make exponentiation work. So if we take a number and we want to encrypt it, we have to take that and then exponentiate in our ring, which will take k bits. So that's k squares, and then up to k multiplies. So we have 2k operations. Each of these squares and multiplies will need to be reduced modulo n, which is a k-squared operation. So our total idea of how many operations this will take if we scale up is k to the power of 3, assuming that we already do this squaring optimization that we had earlier. If we didn't, it would be k faculty. So k factorial, that would be crazy. So this is still going to be very big. If we have 24 bits, or 1024 bits, we'll have 32,000 operations. If we go for the largest version, we have 110 million operations. I've implemented this and tried to connect to Google. And the problem is that you get disconnected before you get the verification that the public key is correct. So as much as I'd like to say this is RSA, it's not. We need more. We need a trick called Montgomery multiplication. And this is a mathematical trick. You'll need to look up the details. I've included the link again, where if we take the numbers modulo n, we can change them over to a different ring, modulo n prime, where n prime is bigger than n and n prime is a power of 2, like, at 2048. And then reducing that modulo this power of 2 is trivial because we multiply them and just ignore the rest of the results. And then patching that up to get back to the original number is also doable, which means that given this optimization, we can now do this about 500 times as fast, which means we can actually get a connection. So that's good. So typical RSA in use is a product of two large primes, and E is either 3, 17, or 65,537. And 3 and 17 are considered a bit short for a prime. There's some kind of attack that you can do if you have a very small exponent. In some cases, if you exponentiate something to the power of 3, it wouldn't use a modulus because the numbers are just so big that the entire square or the cube fits in the number. And having a regular square root or cube root, that's a solved problem. So we must make sure that we use this, so we try not to use these. If you look at all practical public keys in your computer, you will find that 95% plus of them have exactly 65,537 as a public key. So we can special case this to make it fast. So where do we get prime numbers? Well, I've tried Google, and it worked well. You can ask it, is 37 prime, and it will say yes. But for large numbers, this doesn't actually work, and we need to make sure that nobody knows what our random numbers are. I've told you mine, so you know how to crack my encryption. So we'll have random numbers, and they need to be cryptographically random, which means about as much as these are not numbers that you can get to by any other means than just happening upon the right number. There's no generation, there's no way to derive it. And we tend to make these things using some kind of entropy. And entropy is a source of information that is unknowable. So in this case, we could use radioactive decay, we can use nanosecond timing of hardware interrupts. Some machines have that built in as hardware random number generators, like RDC on x86 CPUs. And these will get you at least a reasonable amount of random. But what really is random? Have we ever looked at random? So if we want to look at some kind of source and see if it's actually random, we can do some randomness test. We can take the numbers that come out and convert them into brightness values, and put them on a square. Doing this is extremely unrigorous, so mathematicians really hate this, but I love it because it's so intuitive. There's a nice page that has a couple of examples of this. We can take two random numbers and check if the distance from the center is less or more than 1. And if we do this with enough random numbers, you should get pi. Because pi numbers will be within that circle, and the remainder of 4 minus pi will be outside. So this is a way to calculate pi. And we can also use these number pairs to draw on a square, draw lines from each to another, and that will give a specific distribution that should be correct. Or we can go for the full mathematical solution, which is a chi-square test. And there's a whole bunch of other tests to check if numbers are actually random. But we're not doing math here. We're doing programming. So let's look at the squares. So this is random. And in case you're a bit hard of seeing, I've included a magnification of the bottom left corner on the right, so you can see how random this looks. There's no discernible pattern. There's no clear way of identifying this. So what do you think about this picture? It's a bit hard to see on the left for me from this angle, but if I look over here, I'm seeing some very clear vertical lines. This is the Windows rand function. And the Windows rand function is famous for being a 16-bit random number generator, which means that if you use it on a big enough square, it will have repetitions, and it will have repetitions pretty fast. So if you're using this as a random number source, this is going to cause trouble. But it could be worse. Sometimes people have bugs. And remember the RDC function that we had? It uses some bit of internal state for conditioning. And on one particular CPU model, they forgot to save the state if you went to suspend. Which means that if you resumed and then drew this, you would get this. If you're using that as a source for your prime numbers, you're going to get the same prime numbers every time, which is bad. There's another trick we can do with not RSA, but using numbers in a ring, which is a Diffie-Hellman problem. So Diffie-Hellman concerns itself with trying to get some kind of shared secret between two entities without pre-exchanging information in such a way that nobody else knows the numbers. And it sounds like a problem that shouldn't have an answer, but weirdly enough, it does. So if we start, we pick two random numbers. Each side picks 1, the left side picks A, the right side picks B. Whoop, you're backwards. The left side picks A, the right side picks B. You calculate n, which is some number to the power of A or the power of B, send that to the other side. The other side receives your n to the power of A or n to the power of B, calculates the exponentiation of that to its number, which is n to the power of B to the power of A or n to the power of A to the power of B, which by mathematical identity is equal to n to the power of A times B and n to the power of A times B, which means that both sides now have the same information. Let's look at this from an attacker point of view. The numbers that I can see as an attacker flying by on the wire are n to the power of A and n to the power of B. And to get the end result, n to the power of A times B, I would need to have some way of exponentiating the number to the other power, which means that I would need to solve a discrete logarithm on A or on B. And we just discovered that's not possible. Skipping the math. That means that my attacker knows these numbers. They also know n, but they cannot get A or B. Which means that now we have safe communication between two sides. They have a shared key that nobody else knows. And we'll get back to why we want this, because this doesn't quite get us all the way. So going from RSA to elliptic curves. Elliptic curves are a relatively modern addition, as in it's not 50 years old. It's like 15 or 20 years old. And elliptic curves are, put blunt, just a different kind of ring. It functions the same. It has numbers that are more dense. There's more elliptic curve numbers than prime numbers. So the attack that you could do on it is a lot more complicated to figure out which ones there are, because you can't invalidate most numbers by them not being prime. It's a bit more complicated operation, so implementing it is a little bit more tricky, but even then, it's just math. Ask a mathematician for the multiplication operation, and you can get there. The same idea works. The private key works by exponentiation. You use Montgomery math to get it a bit faster. And then we just need to know which kind of curves to use. So I've used all the right curves from Tanja, who works at the University of Eindhoven. and Daniel J. Bernstein, who also works at the University of Eindhoven and I believe Oxford. And they've looked at a whole bunch of curves. So these are the standard curves. We have SCCP 256R1, 384, and 521. That's not a typo. It's not 512, it's actually 521. And this indicates the bit length of the curve. And these are called Weierstrass curves, and they're used in NIST. In the standard TLS setup, you will be using these curves. There's a second curve which is related to this, which is SACP 256K1, and that one's designed to go fast. That one's used in Bitcoin. So we'll not talk about that because we're not talking about Bitcoin. And then we have the two final ones, which are twisted Edwards curves, X25519, which is a 255-bit key, and X448, which is a 448-bit key. And these are designed not to be fast or not to be the standard NIST ones, but these were designed later to avoid all the corner cases that you would get for implementing them, which means that implementing these correctly is relatively easy, and the curves are relatively more safe, but they're not the standard ones in TLS. If you want to know more about why these curves are safe, please feel free to check out the links. So comparing elliptic curves to RSA, elliptic curves are a lot faster to implement. In RSA, we have to every time figure out how to exactly do the math with Montgomery. We have to calculate a modular inverse a naive way before we can use Montgomery math. But in the case of elliptic curves, we can do this pre-compile time or at compile time with cons.expr. Because we know the modulus. Everything is known ahead of time. We can make a whole lot faster code. We can optimize for things that are true in some curves just because we happen to know the numbers. And they have a faster runtime. Mostly because the number 4,448 is a lot smaller than 7,680. While these are comparable in strength, one of them just takes more than 10 times more operations. So we have asymmetric cryptography. Let's go to the next step, which is hashing. But before we go into detail on hashing, we'll need to figure out how to actually make sense of all these bit numbers. Because I've been talking about 256 bits, 1,024 bits, 8,000 bits. What do these numbers mean? And for that, we'll need to look at logarithmic thinking. Because humans are inherently terrible at logarithms. We are just not suited for things that are so different in scale that we are unable to comprehend how big they are. So to start putting things in scale, let's look at some things that we, up to a point, know, like the solar system, which starts at a distance of 1 to Earth, and about 10 to the 5, 10 to the 6 for Alpha Centauri. Well, this is a giant amount of distance, and we've managed to squeeze the entire solar system we're in within 1.5 octave. That's not quite helping yet. How about computers on the internet? So we started in 1981, and we have about 300 computers. Going up to 2013, we have like 1 billion. It's 10 to the power of 7 difference. But even that is not quite as big as we have in cryptography. So going further, earthquakes. We have 0 on the Richter scale, which is barely noticeable. It's not an earthquake because nobody can tell. Up to 9, which is city destroying. And anything beyond that would just take apart a continental plate. So that's as far apart as we can get. But even that's only 10 to the power of 9. Sound, going from 0 being absolutely inaudible. Even a silent room with nothing running is like 20 decibels. And 120 decibels and up is instantly deafening. It's 10 to the power of 12, but we're not quite there. Okay, let's go bigger. Let's take the observable universe. 8.8 times 10 to the power of 26 meters. And the shortest thing we could possibly ever have in a useful definition, which is a Planck distance. 1.616 times 10 to the minus 35. Let's measure the entire observable universe in Planck distances. And that gets us 10 to the power of 61. And as much as I'd like to say that this is a helpful analogy, it's only 10 to the power of 61. And if we are trying to crack, say, SHA-512, that's 10 to the power of 154. Which is still so many orders of magnitude more that this just doesn't make any sense. There's no easy way to make this intelligible. These numbers are too much too big. So let's use a different way. Instead of trying to compare it to some kind of thing that we find intuitive or reasonable or real-world comparisons, let's try the other way around. We'll stop converting to the power of 10 because powers of 2 are more easily defined. And we find the fastest reasonable attack that we could possibly do and convert it to a timescale for some kind of attacker. And given the scales that we're talking about, if we're off by a factor of 100 or 1,000, it's fine. It's close enough. So let's look at a couple of adversaries. So 2022, we have Dave, who lives basically on the street corner. He's your neighbor who's trying to break into your Wi-Fi. And Dave is running 16 computers, 2 to the power of 4. Every computer has 32 cores, 2 to the power of 5, it's 9. And every core, we're assuming, does 1 billion of whatever kind of cracking result we're looking for. It's an estimation. Some things will be a lot slower, some things will be a bit faster. But assuming that we can do this kind of behavior, he will do 2 to the power of 39 results per second. Let's look at the second one, the large company with a lot of money. We'll call him Jeff for the large company with a lot of money. He has 16,384 computers, and every computer has 128 cores, and each core still does 1 billion operations. That's a lot faster. Then we have an NSA-sized adversary, Paul. Director of NSA is called Paul. He has 1 billion computers. We'll assume that he has basically infinite money and as much as he would like, but it's not possible to make more computers instantly than money can buy. Each computer will have 16,000 cores, and each of those cores will do 1 billion operations per second. So let's look at how long things would take to crack. And looking at the things that we thought were safe, all at the top, DES 56, our Dave, with our current day computer, could crack that in about a day, which is not very secure. If we look at Paul, he would do that in 4 microseconds. That would be so insecure that if you had communication with that, he wouldn't need to think about cracking it. He'll just crack all of them because it's so fast. Nobody cares. Now, going down to the things we actually use, RSA 2048 and AES 128 bits, and RSA 2048 is about 112 bits of security, we get to numbers where even Paul will take centuries or millennia to crack it, and somebody like Dave would just, he could try, but the sun would implode before he got there. Now, if you look at the second line, I'm using SHA-1, which is a hash, and I'm using 80 as a strength instead of 160, which seems weird. This is the thing that's called a birthday attack. So I'll need your answers for some questions. I have a class, and there's 30 children in the class. How likely are they to share the same birthday? Any numbers? 50%? 90? Anybody else have a different guess? You are dang close. My intuition said it's going to be like 30%, but it's actually 70, which is a lot. What does this say about bigger numbers? Because we're not doing children, we're doing hashes. So when we do a 32-bit hash, how likely are we to get a collision? And say we're just hashing files randomly, at what point will we get a 50% chance of 1 collision? And it turns out this is about 77,000, or just above 2 to the power of 16, which is half of 32. If we do a 128-bit hash, we get one at 22 times 10 to the power of 18, which is just above 2 to the power of 64. Again, half of the bit length. And this is why some attacks on hashes will use half the bit length, and some of them will use the full one. If we're trying to get any collision, we can do this in half the attack time. And this is why hashes tend to be a bit larger than we typically use for encryption. This is some kind of variation of just brute forcing a number. And the biggest problem is that if you want to have a specific hash, and we'll get into why you want a specific hash, this is not a kind of attack that can do this. So if you want to have that exact hash, you will still need to break the entire hash and do the 2 to the power of 160 or 256 operations to get there. So let's go into the meat of how hashes work. And to do that, I could go either way. Because again, there's a whole lot of math, or there's the analogy that works. So instead of doing math, we're going to use this thing. This is a bit grinder. We put some bits in on one side, and we get bits out on the other side. And the trick is that for this bit grinder, we have some defined properties. We know that every bit in the input comes out in every bit of the output. Every bit of the output is deterministic and based just on this input, but every bit in the output is, as far as we can tell, just random. So given this bit grinder, and there's like at least 8 hours of talk worth in explaining how to make a good bit grinder, but we're ignoring this bit, we're going to the programming bit. We can construct different forms of hashes. The most common one, and the ones that are currently nearly always in use, is called a Merkle-Damgard construct. And in this construct, we start on one side with an initialization vector. We input one block, pass it through our bit grinder. Input a second block, XOR it on that, pass it through a bit grinder. Put in a third block, and pass it to the bit grinder. And that gets us a hash. This almost seems too simple. I used to think that this was impossible to understand, but this is all there's to it. And this is MD2, MD4, and MD5. And at this point, you can probably guess what MD stands for. And it's used for SHA-1 and SHA-2. And if you're wondering, that stands for Secure Hash Algorithm. It's a very, very intuitive name. There's a problem with this construct, because at this output, anybody that sees H3 can calculate backwards what the current intermediate state is just before F. And anybody with that can extend it. So if we know this intermediate state, we can extend something on the end of it. We can put some message after it. There is a mitigation already in Merkle-Damgard constructs that they have a final step to try to obfuscate the output and make sure you don't get back the intermediate stage. But that's been proven to be invertible. Which means that in many cases, if you have some kind of message, we can add stuff on the back and calculate what the hash would be if we knew what your plaintext was without knowing it. That's a problem. So the trick to fixing this is to make sure that our hidden state is not invertible. We can't get it back. And there's two crude ways of fixing that, which is the kind of stuff that I'd love as a programmer to just invent. Either A, we make the internal state bigger, or B, we take the output and take half of it and throw it in a bin. So the first one's the one that we're actually using. We take the exact same construct, end up at the end, cut it in half, throw half in the bin. And this sounds silly, but this is exactly what's currently being used. And this is more secure than just using SHA-2. There are SHA-2 224 and 384, which have sort of accidentally ended up with this property, and two truncated forms of SHA-2 512, which have intentionally gotten this property. This is the kind of version that is less likely to be inverted, which means that people cannot do length extensions. But some people went with the other solution. Instead of just throwing away half your hash, which is stuff that we spend time calculating, how about we just enlarge the inner state? And this is called a sponge construct. So this is SHA-3, and it works almost in the same way, except in this case, we start on one side by XORing in our values, we pass it through the bit grinder, and we only XOR on the top part of it. How big this top part is configurable, depends on how large your output was. And we do this until all the input is put in. And at this point, we call this the absorbing part of a sponge. After that point, we can squeeze the sponge. And we get back some bits of hash. So we take the top part, this is our output. We can squeeze it again, running through the bit grinder again, to get a new top part, which takes some parts of the randomness that's down here, transposes it up here in some kind of way that's pretty hard to get back. And in this case, we can get an output hash that is as big as we want. We can also use this as a random number generator, which is currently not actually done, but it's in discussion. So we've done hashes. But let's get into passwords and hashing, because this is where we often go wrong. Okay, so passwords. Somebody tells us, let's go and make a secure system. People log in with passwords. How do we do this? Well, we make a computer, we store the passwords. That's easy. How do people get broken into? Well, somebody breaks in your office and takes a sticky with your password on it. It takes your password booklet. That's kind of easy. We tell everybody, stop writing your password down, don't put it under your desk, or just lock the office. That shouldn't be that hard. But it's an online system. Somebody can still try to log in. If you're trying to log in, you can try a lot of passwords very quickly. We can fix this by just throttling them back, saying we can't try more than 3 passwords every 5 minutes. And this is going to stop people from being able to crack a password. But at this point, something bad happens. Somebody breaks in and steals our password database. Okay, dang, didn't expect that. Let's encrypt it. Somebody steals our password database, the encrypted database, with the key. Okay, that didn't help. Let's take the key and not put it on the server anymore so that nobody can steal that. Okay, nobody can log in because we made it impossible for the server to get to your password. That's not the way to do it. Okay, let's try it the other way around. Let's stop storing passwords because this is a bad idea. Let's, instead of storing a password, hash a password and just store the hash. You can't get a password from the hash. Oh no, somebody broke in and stole our hashed password database. Do we care? Should we? What can you do with a hashed password? I mean, it's like trying to log in, except without the rate limiting. And we can't rate limit their computer because that's a thing that they control. They can even pre-compute tables of hashes called a rainbow table and just look up what password you have. And the root problem behind this is not the hashing. The root problem is that humans are horrible at passwords. And seeing this, I always wondered, what is the odds of somebody actually picking 1, 2, 3, 4, 5 as a password? I mean, how dumb can you be? So I looked up the 10 most common passwords. It's right there. As is password and QWERTY and a bunch of ones. And these are horrible passwords. Okay, but we're not looking for the worst passwords. These are users that almost deserve to get hacked. Let's look at an average user. I mean, not everybody's this bad. So the average password is 8 characters or less. And 90% of them are attackable with a brute force attack, and they're likely to be found. So this is actually kind of bad. We can actually measure how good a password is in bits, and we just had an idea about how many bits would be secure. So let's look at how many bits there would be in your password. For this, we're assuming that your attacker knows how your password was constructed. So if you took a dictionary word, they'll use a dictionary attack. This is a reasonable way of looking at it because we can assume there's a bunch of attackers and they'll just use all the methods side by side. There's not more than 5 or 10 methods. This will get you your password. So how many bits are in a password? If it's a dictionary word, it's 18 bits. If it's a keyboard pattern, it's 10 bits. No wonder those things are so common. Typical passwords are about 40 bits, which means that our stereotype Dave, who was the neighbor on the corner, could crack your password in about 2 seconds. Okay, 2 seconds is not good enough. What if we tell them to change their password? I mean, we can tell them how to make a good password. We can tell them put a capital in there somewhere. And now everybody takes the first letter and makes it a capital. We can tell them put a number in there. Now their password is ending in a 1. There has to be a special character as well. Now it's going to be password with a capital P, a 1, and an exclamation mark. This doesn't actually make it better. Whatever kind of constraint you have, your attacker can just implement. And the downside is that now your user is going to be greatly inconvenienced because you're trying to log in with the password you're thinking it's going to be, but was it with a capital? Was it with a 1 at the end? Maybe an exclamation mark? Maybe it was the other password? Maybe it didn't have an exclamation mark? Maybe it didn't need... This is not helping. Okay, I know. We're not going to give the option to a user for giving a password. We'll give them a password to them. We'll generate a computer password and take actual random numbers, convert it to characters with like base 64. It's going to be 6 bits per character. We'll make them 12 characters long. It's going to be 72 bits of password strength. And that's actually good. It's a good password. And everybody hates it. Is it the users that are being annoying and bad here? Or is it us? Why are we complaining about short passwords? Why are they bad? I mean, I have a bank card. A bank card has like 13 bits of security. It's a number. Why isn't that being broken all the time? Well, you actually need a card to attack. You need to have an attack on it, which means you need to somehow try it out. It logs after a bunch of tries. And if you actually manage to get some money out of somebody's account, you're going to get caught. You're going to have to pay up in due time. as much as we'd like, we can't take somebody who stole our password database and is trying to hack it to go to jail immediately. It's a nice fantasy, but it's not going to work. So we'll need to do something else to raise the cost for them. So how can we raise the cost of somebody trying to attack our password hashes? Well, we make sure that they can't pre-compute it. If we use a large salt, we basically make it impossible for them to do a pre-computation and make a rainbow table. And we can use a very slow hash function, which is almost an oxymoron, because hash functions are meant to be fast. We're putting in gigabytes and terabytes of data, and they should do that fast. And now we're looking for a slow one. That's going to be weird. So let's look at salts first. What is salt? A salt is a bit of random data that we append to the password in front or behind before hashing it. We are storing these bits with the password, so given anybody's username, we can look up their salt, hash the password, find out the same number. If we want to pre-compute it, you'd have to pre-compute every possible combination of random bits to figure out which one it could be, which means the rainbow table is not now a couple of terabytes, but a couple of yottabytes. And if you know what a yottabyte is, you're not storing that on disk. So that's good, but it only prevents pre-computation. You can still look at any of the passwords and attack that password. So how do we slow this down? We use a thing that's called key stretching. And instead of using a hash function, we're using a hash function a lot. We're taking a hash function, taking the output of it, putting it back in, taking the output, putting it back in, like a lot. 1,000, 1,000,000, 10 million times, as many as we need. So for a typical password, Dave on the corner, if we do this 1,000 times, it's going to take half an hour. If we do it 10 million times, it's going to take half a year. Which means that in terms of somebody trying to crack your password, this is going to make it a lot harder to crack. But in the end, key stretching is not enough of a slowdown to prevent somebody's password getting hacked if they actually have a bad password. You can still just guess. There's nothing that we can do to prevent that. If your password is just 1, 2, 3, 4, 5, anybody can try this and anybody can log in. But at least we can prevent some successful attacks on this. And before we go out and take a regular hash function, iterate it a bunch of times, just trying to get there, there are a couple of standards for this, like bcrypt, PBKDF, scrypt, and Argon2, introduced in various years. There's also one just called crypt from way back in the 70s, which advised doing things like 10 times, and that's not enough anymore. So take any of these modern standards, and your password database will be secure. But at this point, we're basically the crypto geek, having an entirely secure login system. And logging systems are very vulnerable to anybody who has like $5 and can go to a hardware store to buy a wrench to beat the shit out of you. Because if somebody can beat you up and get your password out of you, there's no cryptography that's going to prevent this. And before we think this is a nice idea, this doesn't actually happen, $5 wrench attacks are on the rise. People actually do this. And no matter how secure your password is, this is not going to help against that problem. That's an entirely different class of problem. Let's go to the next section. We're talking about signatures. And signatures are remarkably simple. I always thought this was a really complicated procedure. It's not. You take a document, you take the hash of the document, we just had that. We do a bit of conditioning to make it long enough so that we use a modulus, and we encrypt it with a private key. Boom, signature. That's it. We use a hash, we use RSA, tiny bit of conditioning, that's all. So how do we verify this? We take the document, take the hash, plus the exact same conditioning. We take the signature, and we decrypt it with a public key. And now these things need to be identical. If they're identical, it's valid, which means signature is done. That's good. We're getting faster at this. We're going to be on time even. So if these match, then the signature is valid. But whose public key did we just check? And why should we trust it? Which brings us to the bigger part, which is certificates. And a certificate is a thing like a password that has the public key and the identity of who owns it. So do we trust the public key and some identity information? No, of course not. There's no reason to trust that. Unless the certificate is signed by some other certificate, which has the public key and identity of whoever signed it. But why would you trust that? Well, of course, it's signed with the public key and identity of whoever signed the thing that was signing the thing that we're signing. So why do we trust that? Yeah, we're going in circles. One of them is going to have to sign itself and basically say, I am the source of trust. I am the root of trust. I can be trusted because I am the ultimate possessor of identity. We call them the root of trust. And that's basically like 150 or so worldwide. Those are listed in a certificate authority list, which is shipped with your browser or operating system. And these have all the roots that we trust, and anything signed by them transitively will be trusted, which is going to be fine. So what happens if they mess up? Well, we get fraud. We get break-ins. We get people trying to access their Gmail and figuring out that it doesn't work because their government is trying to interfere with reading their email and trying to read it for them. Somebody accidentally made a private key and a public key with a certificate signed to Google and gave it to the government of Iran. And then the government of Iran could read your email if you tried to log in, which is bad. Somebody else can also mess up. This is a Dutch company, Symantec. You probably know this. Symantec is also messed up because they knew what private keys were meant to be. A private key, if it wasn't clear from the name, a private key is meant to be private. You're not supposed to share it with somebody else. And Symantec said, well, here's a company that is going to sign some certificates for us, but instead of signing their certificate, we're just going to give them a key. And then somebody figured out that that company got hacked, private key was leaked, and then a whole bunch of certificates were immediately revoked. It's a horrible story. Long story short, we are trusting them. We don't like trusting them, but right now it's the best solution we have. So getting to the last bit of cryptography, and to me this was the thing that drew me into cryptography. This is the thing I like most. Symmetric cryptography. Take some bit of data and encrypt it in such a way that you can then get it back if you know the key. It's like a locked box, the thing that always attracts your attention, trying to break into it. So what if we took our bit grinder and we could reverse it? That'd be, well, on one way it would be nice because it would be a very interesting mathematical construct. On the other hand, it would be completely useless. Because the point of a bit grinder is that you cannot get it back. And now we're inverting it, so you can get it back. This is not a helpful construct unless you need a key. And if you need a key to get it back, then we can use this reversible bit grinder to take some plain text, encrypt it to cryptotext, and then only if you have the right key can you get it back to plain text. We'll put these two together because it looks a bit nicer, just like this. And this is how AES works. We have a reversible function. We can encrypt data from one to the other. We can decrypt it back to the other. Before AES, there was a different construct, which I'm going to mention and show because it's a lovely design, where we can use a one-way bit grinder to make a reversible one. And that's called a Feistel network. The idea is that we take our input, split it into two blocks, add the key to one half of it, pass it through a bit grinder, XOR it on the other one. Then we swap the blocks, do the same on the other half, and we swap them back. And now both halves have been encrypted once, but given the key, we can reverse this and get back the output. Because the block that we're using in this XOR is over here. The block we're using over here is over here. We can reverse this function, this Feistel network, and use the keys in reverse order and get the output without much trouble. So if we just make a simple bit grinder, we can make it a reversible one. And this is a design used in DES and a couple of other ciphers. So now, given that we have a reversible bit grinder, how do we use it to encrypt things? Well, we can go for the simple approach. We take the input, shove it through the bit grinder, get an output for every block of input. And this is called electronic codebook. We just take each block separately and encrypt it. The downside is that if we encrypt something that is identical to something else we encrypted, the encrypted output will be the same, exactly the same, which allows us to make a very nice graphical demonstration of how much encryption this is by showing you an encrypted picture and asking you to guess, what is this? I'm afraid you're going to get that. So this is a problem because it means that while we are encrypting our data, the shape of the data and any repeated block is going to be extremely obvious. So while we're encrypting it, it's still not quite enough to hide our information. Beyond electronic codebook, there's an operation called cipher block chaining. And in this case, we take an IV, we XOR it on the input, encrypt it to the output. And then we take our output, XOR it on the next block for the next output, XOR it on the next block for the next output. This is great because it means that our encryption actually looks like this, which means that nobody sees our picture and it's actually encrypted and we can't read it. It also means that it kind of sucks nowadays because A, it is extremely sequential. To do this encryption, you'll have to get the IV, do the first operation, wait for it to complete, do the second operation, wait for it to complete. There is no possible way to do anything in parallel. So nowadays, we just really don't like this anymore. It's not a good way to do things. But there's a perfect encryption. I'm not sure if you've heard of it, but there's a perfect way to encrypt something. And that was in use in the Soviet Union. So what they did was they took a key, and instead of taking a 128-bit or 256-bit key, they went for a huge key, like books full. And they shipped it into submarines. They took the submarine took a part of the key, indicating what part they started, and XORed that with the text they want to send. Now take that bit of data XORed with the key, send it to anybody, and you can come up with literally any possible outcome given whatever kind of key you invent. Which means that there's no possible way to know which output is the valid one. Which means that there's no possible way to break this. And we call this a one-time pad. And up to a point, it's a perfect encryption. Because there's no possible way to prove that any of the plaintext is the output. You can give anybody a key, and if it's the wrong key, they could just read Mary as a little lamb and not know that it's not the right thing. But is it perfect? Not really, because the key must be the same size as your text, which means that if you want to use this, your key better be huge, books full, disks full. And you can never reuse a key. You can never, ever, ever reuse the key. And this is what eventually was a problem in World War II, because at some point in your submarine, your keybook ran out. You're in the middle of an ocean. What do? Either you stop talking to everybody, which means that you're basically a sitting duck and you're going to get destroyed, or you reuse part of the key, which means that somebody else can now decrypt your data. Not going into details on how, but somebody can decrypt this. Which means that now your data is compromised. Somebody can just get your location and you're basically done for. So it's not quite perfect, but it is a big inspiration because the idea of having some kind of random string and XORing it with our data, we can do that with different things, with non-infinitely sized books. We can take something called a stream cipher, which is like a random number generator. And that outputs a string of random numbers, which is good enough as a key. We take the string of random numbers, XOR it with our plaintext, get ciphertext. And anybody with the same generator with the same key gets the same random numbers, XOR it with the output, poof. So what if we did that for block ciphers as well, so for AES? Instead of taking a block and encrypting the block, we'll take, say, the number 1 and encrypt the number 1, giving us key block 1, encrypt number 2, key block 2. Get a sequence of key blocks, XOR that with our plaintext, get ciphertext. And this is something that we do. This is called counter mode, because it starts with a counter. This has the same problem, though, as the perfect encryption. If somebody ever reuses this, the security is hosed. There's nothing left. But it also has a bigger problem. If I'm trying to log in somewhere, it will say my username is baby, my first 2 letters of my first name and the first 2 of the last name. And it will say, that's my username. Encrypt that with counter mode, send it in a cookie to me. Now, my cookie, I can XOR in some bits. And every bit I flip will also be flipped in plaintext with no verification, which means that I can change my username by XORing something to root. Poof, root access, admin access. So this is awesome if you're trying to break something. So what happens if you modify encrypted stuff in things other than counter mode? We've seen counter mode. We can choose a bit to flip, but we're just flipping random bits and we don't necessarily know what we're doing. But we can try a bunch of times. If we do it in ECB, electronic codebook, you just get a block of garbage and everything else is still intact. If you do it in CBC, that block decodes to garbage, but the block after it will be XORed with whatever we did, which means that we can flip some bits in this. There's a nice attack we can do there. So we're not just using counter mode. We have a problem because we know that there's zero integrity. We need something to do integrity, but we already had that. We had hashes. So let's take our stuff and apply an integrity check. So we'll just encrypt and integrity check. But doing this straightforwardly is going to lead to security problems. So the mathematicians came up with a more nice way to do things, and they call it counter mode, which is Galois counter mode or CBC counter mode. And they're basically the same thing. They're an integrated hash into your encryption function. So in this case, we can encrypt something, be sure that we get the right data out. The Galois counter mode is similar math to AES. It's a nice hash. CCM was basically added to TLS as a backup because, well, the Galois hash is a new bit of mathematical construct, and we don't know if it's going to be secure, but we think it is. But in case it isn't, we'd like the world to be able to switch over quickly to something that we trust. We trusted CBC before, we'll trust it for this. So we have a backup. So let's go to TLS. We have a cryptography grounding. We're about an hour in, so yeah, we're good. We should be able to do this. I mean, how hard can it be? So what is a secure connection? If I'm trying to make a secure connection, say to my bank or my email, I'm trying to connect to one other side. There should be one system responding. I'd like nobody to listen in, nobody to change anything, and know that my connection is to that other side. And we had a bit of math so far. Checking the identity of whoever it is easy. We give them a challenge, they send a response, we check the response, we trust them. Making a secure connection is really easy. We can do Diffie-Hellman. But if we want to make a secure connection with a certain identity, that's going to be hard. Because we can make a connection first and then send a challenge response, but somebody can man in the middle of that. Making a secure connection with that specific identity is really hard. And how hard it is, well, nicely illustrated looking at the history of TLS. TLS came from SSL, so this is the full version history right now. We start with SSL v1, which is so broken that they didn't release it from Netscape. They started releasing SSL version 2. Funnily enough, version 1 never actually existed. And that was in use from 95 until 2011. And the problems were, well, numerous. You can man in the middle it, you can do a length extension attack. That's a problem. So SSL v3 came along, 1996. Deprecated and basically terminated in 2015 because it had a thing called Poodle, which is a funny name for something being a plaintext oracle. You could ask it to decrypt some bytes, and if you guessed the right value for one byte, it would send you back a yes, which means you can give it 256 tries and get a byte every time you did. So you could just take your entire cryptotext, feed it incrementally, and get back the entire plaintext. That kind of defeats the point. So we had TLS version 1 and 1.1. These were reasonably good, 1999, 2006. And both of these had an internal assumption that the hash underlying everything would be SHA-1. And if we remember back, this is 77 bits of security. Our NSA-sized attacker could do this. It wouldn't be fast, but they can do this. So it's basically not safe enough. So at this point, we've deprecated SHA-1 and TLS 1.0 and 1.1. We get TLS 1.2 in 2008. And at this point, TLS has accumulated a whole bunch of ideas, a whole bunch of options, renegotiations, changing over from keys. There's a whole bunch of things you can do at runtime that make it either hard to analyze and that offer some kind of attack. And the big problem is that at this point, if you want to make this secure, you take TLS 1.2 with all the right settings. And if you don't do the right settings, it's actually not as secure as you think it is. So in 2018, we had TLS 1.3. And 1.3 is basically 1.2 simplified a whole bunch. So you take out all the optional things, all the renegotiations. We take out compression, because it turns out if it's compressed, the first couple of bytes are known and you can attack that. And we just simplify the protocol to the absolute minimum for a secure connection, which means that implementing it is actually useful and fun, for some value of fun. So in TLS 1.3, making a connection starts with the client sending a client hello. This is the client saying, I would like to connect to this server. These are my key parameters. These are the kind of things I can do. And the server replies with a server hello saying, this is a server. I have these key parameters and so on. Then it sends encrypted extensions, which are some options that it can set. At the moment, it's basically 0, basically empty, because you don't need this. It sends a certificate to show who it is. It sends a certificate verify. And trickily enough, there's already a challenge sent, because it takes everything that happened up to that point as a challenge and uses that as a plain text to provide the decrypted version of. And then we send a finish message, which is a checksum over everything above it. And then the client sends back, it's finished. And at that point, we know they have done a Diffie-Hellman exchange, which is here. Both of those contain a key half. And after that point, at the end of server hello, both of them have a key they can use to communicate. We then send a certificate and a certificate verify, which allows them to ask, which server is this? Are you identified? Is this actually the right server? And checking that this is still a valid certificate. And to check that both of these halves went correctly, so Diffie-Hellman and identity checking, we have a connection integrity check at the end, where we take a checksum over everything above it, both of them, do a cryptographic operation with that, with the key that we now have, send it to the other side, and at that point, both of them trust that the connection is fine. So let's look a bit at the TLS Cipher Strings, because TLS has really complicated strings for saying how exactly a connection should be set up. And if you know that this is how a connection is set up, those are actually reasonably intelligible. Starting from the top, we have ECDHE. This is Diffie-Hellman. EC stands for elliptic curve. We had both of those. And those parameters are sent in client hello and in server hello. At that point, we have a secure key. We then start using RSA in certificates and certificate verify. This is, our certificate happens to be an RSA key, so this is used in the cipher string. We have certificate verify, which is our signature with our key over whatever came before, and that uses SHA-384 in green in the signature step. We then send a SHA-384 checksum in finish both ways, which is done with SHA-384. And the final bit, AES 256 GCM, Galois counter mode, is what we're using to encrypt our communication. And all of these details, up to the point of being able to implement everything, is in RFC 8446. It's a bit of a big one. Seeing this flow, this is just the example flow for how a good connection would work. There's a couple of things that you can still do. You can look in Annex A, which has as much as ASCII can do, a graph of how a server and how a client would do this, including all the options. So if TLS is this simple to implement, because we're done with the TLS part, this is all there's to it. Why is it so hard to implement? Well, the number one problem is that it's so hard to debug. You start implementing something, send it to the server, look with Wireshark, and Wireshark that says that's encrypted data. Can't tell you anything. Server says no. And then you try something else, server still says no. Wireshark still says encrypted data. And when you have it almost done, and you think it's almost going to work, then the server says no only 5% of the time, which means that debugging it is even more of a trouble case. You can export your keys because, well, you're implementing everything, so exporting keys is kind of easy. Import them into Wireshark, and it can show you everything, and this is going to help immensely because it just highlights which parts you got wrong. I'd almost say try this, but it's a couple of months of work to do this, so if you have time. Then the question is, do you want to do TLS 1.2 or 1.3? 1.2 is a lot more complicated. 1.3 is about as complicated as we just saw. But it's only 60% of servers that support it, and not all clients like it, which means you'll be cutting off anybody from 2019 and before, which is relatively recent. And then the question is, which of those cipher combinations will you implement? And again, TLS 1.3 is a lot nicer. TLS 1.2 has like 50 options. TLS 1.3 has 5. And only one of them is required, which means you can do that one and it will work everywhere, guaranteed. It's pretty nice. So let's go into some detail about cryptography, because so far we've been looking on the constructive side. We've been making things, we've been constructing things. We need to understand how an attacker looks at this to understand how they can attack what we're making. So we have two sides to attack cryptography. We have the theoretical side. We have cryptanalysis. That's a method of trying to figure out how a specific bit of your keys or your plaintext gets through the algorithm to a certain level, trying to find a place where you can make a non-50-50 guess at the value of something. And given a non-50-50 guess, and cryptographers like to have just 50.05 that's good enough, they can start expanding on that, repeating it, doing a whole lot with it to make it a 90 or 100% attack. We have differential cryptanalysis, which is a slightly more complicated version of basically the same thing. And then we have design failures. Sometimes people just mess up in cryptography design and have something called weak keys or different kinds of attacks that just didn't work as they thought. And then we have the practical way of attacking things. We can brute force. If you have a cryptography with 40-bit keys, just try all of them. I mean, it's a lot of keys, but your computer can do it fairly quickly. We can leak information, just trying to do an operation, and if it finishes quickly, that means that the number that was put in is relatively small. And we have implementation bugs. Before we go into the examples for practical attacks, let's talk about broken crypto. Who knows what broken means? It's a really weird term to use because unbroken cryptography can be completely useless and broken cryptography can be perfectly fine. The term is a mathematical one, it's not a functional thing. Unbroken cryptography means that brute force is the fastest thing you can do. Just trying all the keys and seeing which one gives you the result that you're expecting, that's the fastest attack possible. If that attack takes 3 seconds, it is not broken if it's still the fastest. Broken cryptography has an attack that is faster than just brute forcing all the keys. You can do something clever to get keys much faster. And in some cases, this is an order of magnitude or a couple of order of magnitudes. In case of DES, it's about 10 to the power of 4, 10 to the power of 5. So 10,000 or 100,000 times faster than brute force. In some corner cases, this could be just reducing an attack surface from 2 to the power of 80 to like 10. So looking at DES and knowing that it now has an attack of 2 to the power of 43, how hard would it be to break it just by brute force? So DES is from 1975. It used to be the data encryption standard up to 2002 when it was replaced with AES, where DES is an acronym for data encryption standard. And AES is replacing it because it's more advanced, so that's the advanced encryption standard. It's not just programmers that are bad at names. So if we want to brute force DES, we just try all the keys. There's 2 to the power of 56 keys. And if you can recognize which of those produces the valid output that you're looking for, you can see which one of them it is. In 1977, that's 2 years after it was invented and publicized, there was a conceptual design from Diffie and Hellman, the people that made the Diffie-Hellman algorithm, that could crack it in a day. If you have 20 million, you can build this machine, crack the entire DES algorithm for one particular key and one block of data in a day, which is remarkably quick for something meant to be secure. In 1998, the EFF, Electronic Frontier Foundation, made a machine called Deep Crack, and they could do it in about the same time for 250,000. And in 2006, somebody just started offering it as an online service. You can just send them some bit of data, and they would send you back the decrypted results based on relatively cheap machines. So if you want to crack DES, it's just a matter of sending somebody some money. We've touched upon the idea of an oracle. And if you're doing attacks, oracles are a concept that is important to use at some point. So an oracle is a thing that when you're trying to make an attack, you need to have some way of figuring out information. And if we're talking about Alice and Bob, if one of those is able to send you back data about a block trying to be decrypted, so say we mess with something, we send the block there and get an answer back, if they can tell us whether the first byte was correct or not, we can use that as an oracle to get information about the private key or information about plain text. So an oracle is an unwilling or unaware participant that we are able to use anyway to get something broken. One of the things you can do about preventing yourself from being an oracle is logging when somebody sends you corrupted data. And I've included a bunch of CryptoPals challenges. This is a challenge where you can implement these algorithms yourself, and then they tell you to basically implement AES encryption with CBC, as we indicated, we talked about like an hour ago. And the challenge is to attack your own crypto system, given an oracle function, and just completely break it. It's a lovely way of realizing that given the cryptography primitives we had, you can still mess up greatly. Then the next big challenge is constant time computation. If we have a private key that's actually really short, exponentiating it is going to be quick. If we have a big private key, then that's going to take a long time, which means that we're leaking information about our private key. And if we have the same timing in every possible path, you're not leaking information. But it's really hard to do this, especially in implementation. If we look at RSA, we implement it by taking our current value, we square it. If the current bit is set in our private key, we multiply with the accumulator and reduce modulo the polynomial. And while not all the bits are set, we repeat. This is extremely not constant time because we have two big things. We have if and while not all bits are set. While not all set bits are done. This means that if somebody can check how long we take, they know how many bits are set in our private key and or how long it is. And in some cases, they can figure out our private key using this side channel information. For a 4096-bit private key, we'll do 5,900 operations estimated. And the private key we could do in 18. You can tell the difference between those two, but it doesn't quite leak the private key yet. If we want to implement this in a constant time way, then we'll have to do something else than an if statement. We'll have to multiply the accumulator with either the squared value or the constant 1. And then the multiplication of that number with 1 will need to be constant time as well. So we'll need to treat 1 as a 4096-bit integer and take a really complicated way of multiplying it and reducing it modulo the polynomial, knowing full well that it doesn't do anything. And then we'll repeat that exactly n times, which is the number of bits. Even if we know that the rest is just zeroed, we'll need to take the full time not to leak information. The big problem here is that we have a compiler, and compilers are really good at making things fast. And if it sees that we're multiplying with 1, it's going to get rid of it. And now our constant time computation is not constant time anymore. There's a possibility of using cache timing, but I'm going to skip ahead a little bit. We'll skip over the cache influence timing, and we'll go to Heartbleed. Heartbleed is an implementation bug, and it's one of the nicest ones to look at. It's somebody sending a request for a ping. You send a request for a ping, the other side sends a reply. And it both had a field that said how long the ping is, and it had a wrapper, which said how long the data is that you're sending in the ping. So you can actually send 8 bytes and indicate in the length field that it's 65,000 bytes, and the reply sends you 65,536 bytes. Whoops, there goes a private key. And yes, this has leaked a whole bunch of private keys in practice. Other challenges are that we have private keys in memory. We need to somehow prevent somebody from accessing our private keys, reading them from disk, reading them from swap space. This is actually kind of hard. So practical security, an attacker needs to find one flaw, and a defender needs to get everything right. If you make a minor mess up, you will be caught. So the final bit, let's learn from everybody else's mistakes, because history is nice. In 1997, somebody published a paper on how to make a random number generator with a backdoor. And in 2004, the NSA designs dual ECD RBG and pays $10 million to RSA to make this the default random number generator. 2006, NIST, the National Institute of Standards and Technologies in the US, publishes a requirement document saying that if you want to have our government approval, you will need to implement this. And in 2007, Bruce Schneier, one of the more famous cryptographic people, publishes an article, did the NSA just put a secret backdoor in the new encryption standard? And then a whole lot of nothing happened. Most cryptographers didn't like it, but it's still implemented. Until 2013, when somebody called Edward Snowden leaks a document. And in September, people found out that it had a program in it called Bull Run, which was meant for the NSA to covertly introduce weaknesses into encryption standards. Basically saying it's exactly what you think it is. 3 months later, the RSA recommends, please don't use this anymore. And the NIST says, please stop using this because, yeah, it's kind of backdoored. It's a random number generator. And if we know what numbers we can generate, we know what RSA keys you're going to get. And we can crack anything that uses actual random numbers. It has a parameter called Q. And given this parameter, if you know how it was made, you can reverse the state from the output. So you could generate whatever output comes out of it. So seeing a public key or a random number, you could just guess their private keys. And nobody knew where this number came from except for the NSA. So how bad is it if you can guess some random numbers? So we go to the PlayStation 3. The PlayStation 3 had a signing system on it that would make it so you couldn't run any code on it. And the signing system requires you to use a random number as part of encryption. And Sony implemented a random number by making a function that says this is the random number. It's a constant random number, which means that it got hacked. And using this method of not having a random number allows them, using a whole lot of math that's explained in detail, to just reverse the private key out of the machine. The private key that you can use to sign everything and that they can never remove. Whoops, there goes a private key. But we can get rid of private keys and accidentally leak them much easier. The NSA in 1993 introduced a thing called a Clipper chip. And this was an idea where they thought they are going to protect you. They are the benevolent NSA and everybody's going to trust them. We're going to keep the algorithm a secret. Here's a chip. It has a private key. We have a backup of it. And we're just going to keep it secret. We're not going to mess around with it. And people trusted this as much as you think that they should. So the entire program was defunct by 1996 because pre-sharing your private key with literally the NSA is like the worst thing you could do. And they published the algorithm in 1998. It hasn't been broken yet, which is remarkable for such an old thing. And this is basically it. So I hope you enjoyed the trip in cryptography we've made. Do you have any questions? So the question is, when I'm using OpenSSL, do I need to watch out for something in particular, like not keeping files in memory and loading things? The answer to that is yes, because you will be the one handling private keys. You know where the files are located. And the best thing you can do with that is use an API on your cryptography library that doesn't allow you to load the file yourself. So if you can make the OpenSSL library itself responsible for loading a file from disk, use that approach. In that case, the entire responsibility is within OpenSSL, and we should be assuming that the implementation of that does it well. In that case, you are not keeping the file in memory yourself. A second thing you could do, in case you do have to load it, is to memory map it, and then forcibly unmap it. In that case, you would at least be certain that it is out of memory. But the best way to do it is to use some cryptography library that has implemented it for you. So the question is there an ongoing arms race with cryptography? And the answer is yes, but not with computers as they are right now. Because the logarithmic scales that we had at the start, so knowing that the NSA computers would still be way underpowered for the current algorithms, we kind of know that as long as the algorithms are good, we are safe. I did allude to the quantum cryptography breakthrough, which is Shor's algorithm, which allows you to factor numbers on quantum computers very, very quickly. And if that goes any further, then RSA is basically broken as is. In that case, we will need to switch to either elliptic curve, if it survives, or something else. Beyond that, the biggest thing that we're trying to do is get rid of all the old implementations. So we're trying to make sure that people stop using DES, people stop using SHA-1, and people start using TLS 1.3 and other algorithms and other implementations with these things fixed. Because the biggest problem that we have right now is that many people either don't understand cryptography or don't realize why the thing they're doing is actually not safe. Yes. So the question is, when the service sends a certificate back, how does the client trust it and why does it? So the certificate that's being sent back typically includes a few certificates. It has the bottom end certificate, the leaf certificate for the server itself, and it includes all the intermediate certificates to get to the root, but not the root itself. If it sent a root, we couldn't trust it because it would be self-signed and we cannot trust somebody else's self-signed certificates. We would take all of those in and then try to construct a valid path going from a trusted root to that leaf certificate. And if we can find a valid path, that means that we will trust that leaf certificate for this server. And the certificate verify is the challenge response that makes sure that we know that they actually have the private key that matches the certificate.